All right. So these are the main learning objectives coming from Chapter 1 that you'll be responsible for. Know the difference between descriptive and inferential statistics, meaning be able to, if given a scenario, choose which is which. Understand the differences between a sample and a population, and recognize levels of measurement. And when you come to a question about levels of measurement, make sure that you're paying attention to that it says levels of measurement, and that when talking about levels of measurement, we're specifically talking about nominal, ordinal, interval, and ratio. And afterwards, the entire population is a group of individuals. So if you are interested in, say, fifth graders, that would be your entire population of fifth graders in the U.S. That would be your population. If you're only interested in fifth graders in Austin, Texas, your population would only be the Austin, Texas fifth graders. And it changes depending on what your focus is, right? So a researcher might be interested in the relation between class size and academic performance for the population of third grade children. In this instance, they're talking about third grade children across the United States, right? And a sample is usually just a subset of the entire population that you're interested in. So a lot of times populations are too big to measure everyone. Like if you were interested in fifth graders in the U.S., way too big to measure everyone in the population. So you would select a subset, a sample. So you could take just the fifth graders in Austin being a sample from the larger population of the U.S. fifth graders. Does that make sense? So, descriptive statistics are methods for organizing and summarizing data. So tables and graphs, they organize data, but they don't do any kind of transformation to it. And means, medians, modes, summarize it, but you aren't changing anything about the data. So that would fall under descriptive statistics, and then a descriptive value for a population is specifically called a parameter, and the descriptive value for a sample is called a statistic. And that's a good thing to know, the difference between a parameter and statistic. Inferential statistics, they are methods for using sample data to make general conclusions, inferences about populations. So if you took a sample of fifth graders, Austin fifth graders from the larger population of the United States, and you wanted to tell if there was some kind of difference between the two on, say, academic achievement, are the fifth graders in Austin achieving at a higher rate than the fifth graders across the U.S.? You could do some kind of test, and that would be inferential statistics, because you are trying to make some kind of prediction from your sample data about your larger population. So parameters versus statistics. A parameter is a measurable characteristic of a population. So the mean of a population would be a parameter. The same thing can be said about a sample, but that would be referring to a statistic. So if you got the mean of a sample, that would then be a statistic. So you have a population of 1,000 college students, and your population parameters are the average age is 21.3 years, the average IQ is 112.5, and 65% are female and 35% are male. So you took one sample of 5, and the sample statistics are different than the population parameters, a little bit different. The average age is 19.8, the average IQ is 104.6, and it is 60% female and 40% male. And then you took another sample of 5, and your sample statistics are different again, because you're pulling from this huge population, your samples are going to be a little bit different than your population parameters because you're not pulling everybody in the population. So this one has an average age of 20.4 and the average IQ of 114.2 and is only 40% female and 60% male. So if we were to conduct a research on general well-being of college students, the participants are likely to be what? Somebody. A sample or a population? A sample. Yeah. And if these results show that 40% of the college students are overstressed, this characteristic is what? A statistic or a parameter? Yay! All right, and the difference between a sample statistic and a population parameter is called sampling error. So here, these differences between these two samples is sampling error that correspond to the population parameter. So a lot of what inferential statistics is about is measuring and defining how large and the role that sampling error plays in our inferences. So there are 4 levels of measurement. You need to be able to recognize each of these. So if given a scenario, be able to say whether it's nominal, ordinal, or interval or ratio. So customer service rated as superior, average, and poor, what would that be? Exactly. Interval. The difference between interval and ratio is the 0 points. So an interval level measurement will have all the same characteristics as nominal and ordinal, but it's adding the equal spacing. So inches on a ruler, you know that 1 inch to 2 inches is the same distance as 2 inches to 3 inches, right? So that's the equal interval. If you looked at winners of a race, a track meet, the difference between first place and second place isn't necessarily the same as second to third. So that would only be ordinal. Ratio has all the characteristics of the levels below it, but it also adds a meaningful 0 point, meaning that it's not arbitrarily placed on the scale. So Fahrenheit and Celsius arbitrarily place the 0 on the scale of temperature, right? 0 degrees in Fahrenheit or Celsius doesn't mean a complete lack of temperature or chemistry, people, lack of movement in the atoms, right? But in kelvins, 0 does mean a complete lack of movement in the atoms, therefore lack of temperature, right? So kelvins would be in ratio level measurement, but Fahrenheit and Celsius are only interval. Makes sense? So the properties of nominal level data is that you can name it. They can be counted. There's no ordering to it. The labels don't mean anything other than what they are, like male and female. You can't say that one's better than the other, right? What workers want. More money, better health care, better retirement, work-family balance. Like, there's no way to put that in an ascending or descending order, right? Ordinal level data, you can. So there is some kind of order, high, medium, low, superior, good, average, poor, inferior. Like there's a way to order them, first, second, third place, right? But that's it. So you've got labels and order. Interval has labels and order and adds, the equal spacing in between the intervals. So dress size, some could argue this, should be the same between size 8 and 10 as it is for 10 to 12. And ratio has all of the properties of the levels below it, along with a meaningful 0 point. So height. So it doesn't make a whole lot of sense to say that like you or I have no height, right? But that 0 point does mean something. Like if you were measuring something, a piece of paper, it doesn't have much height, much measurable height. So that 0 is a true 0 point. It's not arbitrarily set on the ruler, you know. But sometimes it doesn't make sense to think about stuff like that. So, chapter 2, know the summation notation, be able to read a distribution table, be able to find out the mean for the distribution table, and understand the concepts behind different shapes of symmetrical and skewed distributions. So, a frequency distribution table consists of at least 2 columns, one listing the categories of the scale of measurement, so your x's, right? And another one for the frequency, how often each score occurs. In the x column, the values are listed from the highest to the lowest without skipping any. This is called an ungrouped frequency distribution. A grouped frequency distribution would just group them like 1 to 4. And then 4 to 6. But you don't have to worry about group frequency distributions. So for the frequency column, it's just the tallies of how often that occurred. And to find the total number of occurrence of observations, you add all of the frequencies to get your N, capital N. So here is a frequency table for qualitative data, where you have mutually exclusive categories, meaning that somebody can't be grouped into 2 different categories. That's what mutually exclusive means. And this is an example of a grouped frequency distribution where you have 200 up to 600 and the frequency of how often that occurred. So the class intervals, don't worry about the midpoint or lower or upper limits. And if you wanted to construct one, you would basically come up with something like this. And you could either do tallies or you could just put the actual numbers in there. So you will not have to construct any tables, but you will need to know what the different columns mean and how you would calculate it. So you have your scores on the left side, and then your frequencies, and then the percent, which is also called the relative frequency, RF. And the way you calculate the RF is you find your total N by summing all of your frequencies and dividing each row's frequency by the total. And that gives you the proportion that fall into that row. The cumulative frequency, all you do is add them as you go up. So you would just transfer over the one on the bottom row over to the cumulative frequency column, and then add the one that's in the frequency column for a score of 1 to that one that you have at the bottom, and then keep doing that until you get up to the top. And for cumulative percent, it works kind of the same way. So you would take your percent, 0.03%, that's for a score of 0, and just transfer it over, and then add the next one up to it, which is 0.03% also, and that becomes your cumulative percent for a score of 1. And then you keep doing that, and with a little bit of rounding error, you should get up to 100%. And here's a, oh, going the wrong way. There we go. So what is the total number of scores for this distribution? There's another way to do it without adding it. Exactly. So if you look at your cumulative frequency, it will also tell you your total number of scores. And what is the mean for the same distribution of scores? All you would do, well, you could just add the numbers in the bottom and divide them by 36. So, anybody get it? Should be 6. And for the above distribution, how many individuals had a score of 9? 3. Yeah. So if you wanted to know how many people scored below 8, which column would you look through? Yep, and it would be 72% scored below 8, which I just pulled straight from the score of 7 column. If you wanted to know how many people scored between 4 and 8, you would add the relative percent columns for 4, 5, 6, and 7. And that would give you how many people scored in between there. So here's some summation notation formulas. Just keep in mind your order of operations. So anything in the parentheses you're going to do first, then exponents, then multiplication and division, and adding and subtracting. And if this bothers you, don't think of it like this. Think of it more like the example. So like when we get to calculating a standard deviation and variance, go by that instead of these. So the shape, a graph shows the shape of a distribution. So you can have a symmetrical one that looks like a bell-shaped curve. Everybody knows what that looks like. Basically mirror images if you folded it along the mean. Skewed distributions look different. So a positively skewed distribution, I always think of it because it seems backwards, is that the tail is pointing out towards the positive end. If you have a regular distribution with an x and a y, your positives are going to be on your right side and your negatives are going to be on the left side. And if the tail is being pulled out to the positive end, that's a positive skew. If it is the other way, you have a big hump on the positive end and the tail is getting pulled off to the left, that's negative. This negative skew. And they look like this. And that's because your mean, if you have a few people with really high scores, you're going to have your tail be pulled towards the positive n, and the same thing for the negative skew. And then the top right one is a bimodal distribution. So you could have two modes. So if it was symmetrical, if it were a symmetrical distribution, what would that tell you? Basically that about the same amount of people are on either side of the mean. So it basically splits it 50-50. If it's a positive skew, that's telling you that a lot of people got lower scores and a few people got really high scores. And you flip-flop that. If it's a negative skew, a lot of people got really high scores and a few people got really low scores. Chapter 3, you need to be able to explain the concept of central tendency, identify and compute the mean, determine the mean, median, mode, and as well as computing a weighted mean, and compute and explain the variance and standard deviation. So central tendencies, these are measures of location, meaning the weighted mean, regular mean, median, and mode. So it tells you like basically what the distribution looks like and where the center point is. And these are the 4 that we'll be considering. So the population mean is the sum of all of the population values divided by the total number of values. Right? And it's represented by mu. Big N is the number of population values. X represents any particular value or score. And sigma is indicating to sum them. And that's the formula for it. So the properties of the mean. Every set of interval and ratio level data has a mean. So you cannot compute a mean for interval or not interval, ordinal or nominal level data. It just doesn't make any sense. All the values are included in computing the mean. So the mean is unique to whatever set of data that you're using. And the sum of the deviations from each value of the mean will always equal 0. And that's because it's a balancing point. So the mean is computed in a way where it's in the middle and it balances them. And you can see real clearly that if you sum these deviations, -2, -1, and +3, it's going to equal 0. The median is the midpoint of all the values after they've been ordered from smallest to largest. So you have to order them first. It's unique for each set of data, and it is not affected by extremely large or extremely small values. So if you have a set of data that has outliers or extreme scores, the median is better to use than the mean. It will give you a better idea of what the middle point is. And it can be computed for ratio and interval and ordinal level data, but not nominal. And don't worry about number 4. So, after you arrange these 5 college students' ages in ascending order, the median is the middle score, 21. If you only had 4, the heights of basketball players, you would average the 2 middle numbers, and that would be your median. So here, don't worry about upper and lower limits, real limits. So if a population has a mean of 5 and 1 point is added to each score, what is the mean for the new distribution? You just add 1 to 5. So your new mean would be 6. If a distribution of scores has a mean of 10 and 1 new score is added to the distribution and the new mean is found to be 8, you can conclude that the new score was below the mean. If you knew the number of scores in this distribution, you can figure out what the actual new score was, but without knowing that, you can't say anything other than it's less than what the mean is, or mean was. So here's an example. Facebook is a popular social networking site, and a sample of 10 adults revealed they spent the following number of hours last month using Facebook. Find the median number of hours. So the first thing to do is put them in ascending order, and then you would come up with 5 plus 7, or 5 and 7 are the two middle numbers, divided by 2 would give you 6. And the mode is just the most frequently occurring. So here, distance in miles between exits, 1 mile is the most frequent. It happened 8 times. And that's the same thing. So this is good to know. If you have a symmetrical distribution, your mean, median, and mode will always be the same value in the center. If it's a positive skew, it will always be, the mode will be at the peak of the distribution, followed by the median, and then the mean towards the positive end of the distribution, right? And then for negative skew, it's just the opposite. Your mode will always be at the peak, but the median and the mean will be towards the negative side of the distribution. Range is just the spread. So you just take your highest value and subtract your lowest value from it. And for this example, it's 60. So this doesn't really tell you a whole lot, because you could have, you know, 1 score of 2, and then your range would jump, but most of the values are still around the center. Variance and standard deviation. So variance, and this is for a population, variance is the mean of the squared distributions, deviations from the mean. And standard deviation is just the square root of the variance. Neither are ever negative, and they're only 0 if all of the values in your distribution are the same. For populations who have lots of values near the mean, the standard deviation and variance will be small. If they're really spread out, you're going to have a large variance and a large standard deviation. So variance and standard deviation use all of the scores, making it a better, giving you a better sense of how much the spread is, instead of just using the highest and the lowest score, like the range. And here is the formula, where sigma squared is the symbol for the population variance, and just sigma is the population standard deviation. So the steps in computing the variance: first you find the mean, then you subtract the mean from each observation. Those are called deviations. Then you square those deviations and sum all of them, and that's called the sum of squares, and it's represented by capital SS, and it's the sum of the squared deviations or differences from the mean. And that would give you, and then you divide by the number of people in your population, or widgets, or whatever it is. And that gives you the variance. So here we have the number of traffic citations issued during the last 5 months in this county, and you first find the mean, and then you would subtract that mean from each of the observations, and square it, each one of them, and then sum those. So here they did that. And your total sum of squares for this is 1,488. Then you divide your sum of squares by n, which is 12, because they took 12 months, and your variance is 124. The only difference between population variance and a sample variance is the denominator. So here you have n, and for your sample you have n minus 1. And sample variance and standard deviation are represented by lowercase s. Capital M is the symbol for a sample mean, and lowercase n is the symbol for the number of observations in the sample. And here we have hourly wages for a sample of part-time employees at Home Depot, 12, 20, 16, 18, and 19. So first they calculated the mean, and then subtracted the mean from each observation, squared those deviations, summed them, which gives you a sum of squares of 40, and then you divide that by n minus 1. So divided by 4, and that will give you a variance of $10 squared. So variance gives you a sense of what the range is, but it's not in the right units. So they're all squared so that we don't get zeros when we sum our deviations. You get a sense of what it is, but because it's not in the right units, it's not really helpful. So that's why you want to find the standard deviation, which is just the square root of the variance. And the sample standard deviation symbol is S, and all of the other stuff is the same. So the standard deviation is commonly used as a measure to compare the spread in 2 or more sets of observations. So biweekly dollars invested in Dupree Paint Company in Georgia and Texas. So you can say that Georgia, because it has a lower standard deviation, most of the people are investing around the same amount, around the mean amount. Whereas in Texas, there's more of a spread. There's more variability in this set of observations. And that is it. So anybody have specific questions? Yeah.
When he uses the term weight,
Uh-huh.
what is that exactly? Is it EX? Is that what its equivalent?
EX.
Does that make sense? So all of the...
When you're calculating a weighted mean? So basically on the top, you, say you have a mean of $10 an hour, and 5 people get paid $10 an hour. But you also have 10 people that only get paid $8 an hour. So you want to weight your mean to reflect that you have more people making $8 an hour than your 10. So the top of the formula is going to be the number of people that make $8 or $10 times that amount plus the number of people that make $8 times that amount over your total number of people, right? So it would be 5 times, what did I say, $10 plus 10 times $8 over 15 to give you your weighted mean.
Right.
So I think that's what he was using those symbols for.
Like one of the sample questions in class, he was asking what the weights were. Like he labeled a variable the weights.
Yeah, because he was doing unemployment rate, right? I think so.
No, not that one. It was like a X, that XX columns, the frequency and the number, and he was saying what are the weights, and you like, does that make sense? He labeled a variable the weights, and I don't know what the weights are considered, like what I would add up to get that variable that he wants us to identify.
It'd be the number of people or things,
okay, so
right?
The total number?
Not the total number, the number at whatever one of the rows that he was talking about, right? So if you're looking at a frequency distribution and you have your scores, your X's, and then you have your frequencies, and you want to find the weighted mean for people that scored 85 and people that scored 95, right? You would take your frequencies, that would be your weights, and the score would be your X. Uh-huh.
So weight is just the number of
Observations.
Okay.
Is
Just
another
the
way to say it.
frequency.
Yeah.